Okay, so here we have a much nicer graph of the heating curve of water. So the important thing is that you get these plateaus, and the plateaus occur, ding, 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 at 100 for water, because what's water doing up here at 100 degrees?
Turning into gas.
It is turning to gas. It is evaporating. Okay, what's water doing down here at 0 degrees?
Turn to a liquid.
Melting.
Melting, yeah, it's turning from a liquid to a solid. Now, wait a minute. You guys lied to me. It's
Condensing?
It could be condensing, right? It depends on which way you're going in the graph. Are you adding energy and so you're evaporating, or are you subtracting the energy out and condensing back in? So the same thing is true down here. You could be melting if you're increasing the energy, but if you're sucking the energy out of the system, then you're actually freezing. So this is another way to say this is also your freezing point. Oops, now I'm getting all laggy again. Okay. But that always occurs. Boiling and condensing occurs at 100 for water, and freezing and melting occur at 0 degrees. Okay, now let's clear that out. Now, these flat parts of the graph, whenever we have a phase change, they are given by an equation, Q equals M times HF, which I'm going to write out a little differently. Moles, oops, that doesn't look like a mole. Mole times your delta H of, this one is called fusion. So I just made a video this morning where we talk about delta HFs, and delta HF actually stands for formation, which is not what's happening here. This is fusion, basically the formation of the ice. The ice is coming together to fuse into a solid. And that has a number associated with it, which you would look up in a table. So it's going to be in kilojoules per mole. And when we multiply by moles, I'm going to get heat in kilojoules. Does that make sense so far?
Yeah.
Mm-hmm.
Okay, that's also going to be true here. Q equals moles times delta H, but it's not going to be fusion this time. We're going to actually vaporize things. So it's going to be the delta H of vaporization. Sorry for the handwriting, my thing's weird. Okay, so we've got this Q equals moles times our enthalpies and these two flat parts. But the slanted parts have a different equation, which you might have heard before. Q equals M times C times change in temperature. Have you ever seen that?
Mm-hmm.
Okay, so this is mass in grams. Okay, this, what's Q?
Energy.
Energy or heat, yes. C is a constant called your heat capacity. Oops. Your heat capacity, and delta T is
Change in temperature.
change in temperature. Your ending temperature minus your beginning temperature. So your heat capacity basically says, like, look, my example for people is if I hand you a quarter, you're going to be like, wow, thanks. Thanks. I guess that's really nice of you, right? But when my children were like 5 years old, if I gave them a quarter, it was like, oh my God, this is the most amazing thing ever, because now I can stick it in the machine, get some gum, or I can like go buy something. It was like that. I was amazingly like gifting them with this quarter. So the question is, like, if I give you a quarter, how come your reaction is different? And that's because you have a different capacity for money. right? That to a 5-year-old, a quarter is amazing, but to a 16-year-old, 17-year-old, like, who cares? It's a quarter. Heat's the same way. If you push heat into a material, some materials, boom, they get hot. They're like, whoa, heat, I'm getting hot. And other materials, you push the heat in, and they're like, whatever. Maybe I'll warm up a little bit. And that is called your heat capacity. So how much heat is required to like lift your temperature to a higher temperature? And that'll depend on the material itself. Does that make sense?
Yeah.
Okay, so that equation applies every time the graph is curved. So it's going to apply here where the graph is curved, and this equation will apply here where the graph is curved. All right, the only difference is that your heat capacity is different down here. If this is water, what do we have way down here where it's negative 20 degrees?
Solid.
Solid. Yeah, I'm going to call that ice. You can call it solid if you want. So that's solid. The solid water will have a different heat capacity than your liquid water or than your vapor. Okay, so each one you'll have to look up. There'll be a table that tells you, look, if you're talking about vapor, you have to plug in the specific constant for the vapor. Does that make sense?
Wait, so does heat capacity also like differ from element to element, or is it just
Yes.
like,
Oh, like, yeah, element to element and like compound to compound. So there are going to be huge tables. It's easier to just Google them and say, like, what's the heat capacity of frozen water? On a test, they have to give you these constants. So like before, Sammy, you and I were talking about like how hard is thermo. It's surprisingly easier because College Board has to provide you with a lot of stuff. Like if they want you to solve these problems, they have to give you some constants. They have to give you like a whole bunch of information, which tends to like remind people, oh, they gave me that constant. I'm supposed to use this equation. Like, aha, it helps.
yeah,
Now, in a normal year of chemistry, you would solve a problem in which you started like way down here at like negative 20 degrees, and I want you to heat it up to 115 degrees, let's say. And people say, well, what equation should I use? Because I'm not on a flat part and I'm not on an angled part. So do I use this equation, the Q equals MH, or do I use the Q equals MC delta T equation? And the answer is yes. You would actually have to solve one problem, two problems, three problems, four problems, five problems. It's 5 separate math problems for how much energy it would take to increase the ice. So you would solve this Q equals MC delta T for this section and get an answer. And so you'd plug in your answer. And then you'd solve for this section. You'd have to convert your mass into moles and then multiply by the H, which they would give you. And you'd get an answer there. Then you do Q equals MC delta T for this part again, but with a new C, because now we're in liquid water. So you get that answer and you add it to the previous 3. And then you would use Q equals M times delta H, come up with an answer, add it to those. And then finally, Q equals MC delta T again for this top section. College Board, AP Chem, we do not do that. That's a huge math problem, and they're not interested in the math, really, believe it or not. They just want to know, do you know when to use this Q equals MC delta T equation, which is only on the slanty parts? And do you know when to use the Q equals MH? I'm going to change my color here. Um, let's keep that in red. So you use this, oops, use that equation anytime you're on a flat part. So you would use that equation here and up here where it's flat. So that's the only trick. There's two equations. If you are flat, you use the Q equals MH, and if you are slanted, you use the Q equals MC delta T. And then people will say to me, that's so confusing. I have no idea. Like, what is, So here's how you figure it out. Let's say I mess up, and let me erase a bunch of stuff here. Big, okay. Let's say I get confused. I can't remember. I know those two equations because they're on the equation sheet. You don't have to memorize them, but I don't know when to use them. So I'm going to try and use this equation in the wrong spot. Okay, so I'd say solve for Q. They gave me a mass. Oh shoot, I could look up some C. So I'd look that up in a table, and then I'd say, well, what's my temperature change between here and here?
0.
0. Boom, that would be a 0. So you're telling me that no heat was exchanged going from like the liquid water to steam. And the answer is no, that's ridiculous. So the reason you can't use this equation here is because it's a temperature like constant, but there is energy. So if the energy is not going into changing the temperature, what is the energy doing?
Changing the state of matter.
Changing the state, right? And this H here, that is the change in state. Like that's what this function is for. Like how much like energy is required to change the state. Now let's do it backwards. Let's say I like mess up and I want to try and use this equation, the Q equals MH here. So you're like, well, I can find moles because they gave me a mass, and I can look up my H. That's a little more dangerous because like there's a temperature change here, but you don't notice it. So you're most likely to mess up using this equation in the wrong space. This equation is only when temperature is constant. Does that help? Where
Yeah.
this equation is a dead giveaway. If you use it in the wrong spot, you will get 0 as your answer, and you should know like, oh, the answer is not 0. Where this equation, you do need to memorize. This is only true when like there's a change like chemically going on. I'm going from a solid to a liquid. Where here, I'm staying a liquid. I'm just being a hotter liquid. Like that. Okay.